Hello everyone, welcome to this class. Today we're gonna learn about first order reaction. For a first order reaction, we can write the rate expression like rate is equal to rate constant multiplied by concentration of reactant power 1. Here 1 is our order of the reaction. Some examples of first order reactions are decomposition of nitrogen pentoxide into nitrogen dioxide and oxygen. Reaction between nitrogen dioxide and carbon monoxide gives us nitric oxide and carbon dioxide. All kinds of radioactive decays will follow first order kinetics. Decomposition of hydrogen peroxide into water and oxygen. Inversion of cane sugar in acidic medium gives us glucose and fructose. Thermal decomposition of ammonium nitrate gives us nitrogen and water. Ester hydrolysis in acidic medium will follow first order kinetics. Decomposition of phosphine gas will give us phosphorus and hydrogen gas. And the conversion of cyclopropane into cyclopropene is another example of first order reactions. Now, we will derive some expression for first order reaction. Let's take a reaction A gives us products. At the starting of reaction, the initial concentration of reactant A is small a and the concentration of products is zero. After time t, the drop in concentration of A is small x and the increase in concentration of products is x. So the remaining concentration of reactant A is small a minus x. As this is a first order reaction, we can write rate is equal to rate constant A multiplied by concentration of A power 1. We can write an expression like negative sign change in concentration from change in time is equal to rate constant K into concentration or 1. So we can write dC upon C is equal to negative sign K dt. Now we will integrate initial concentration C0 to final concentration Ct after time t. Negative sign K and we will integrate dt from 0 to t. So here we can write ln c c naught to ct is equal to minus k. So upper limit minus lower limit. So ln ct minus ln c naught is equal to minus k. We can write ln ct is equal to minus kt plus ln c naught. Now we can take ln ct as y, we can take ln c naught as small c, we can take minus k as small m, and t as small x. So we can find the equation of a straight line. It is y is equal to mx plus c. So if we take ln c in y-axis and time in x-axis, we will find a straight line. And the slope of this straight line will be minus k. And the y-intercept will be ln c naught. Now we will take the expression again. Let ln ct minus ln c naught is equal to minus k. So we can write ln ct c naught is equal to minus k. And we can write ct c naught is equal to e to the power minus k. So finally we can write ct is equal to c naught e to the power minus k. So this is our another expression. From this expression, we can see that concentration of reactant drops exponentially with time. If we plot a concentration versus time graph, we can see that concentration will drop exponential. And we can also see that this curve is not touching the x-axis. So we can say that the reaction will take infinite times to complete. And this is our initial concentration C. If we also plot a rate versus time graph, as we know, for a first order reaction, rate is equal to rate constant K multiplied by concentration of reactant power 1. So rate is directly proportional to concentration of rate. As concentration drops exponentially with time, so we can say that rate will also drop exponentially with time. Now we will derive the expression of half-life for a first order reaction. Let's take the expression ln Ct minus ln C naught is equal to minus K. So we can write ln C naught minus ln Ct is equal to Kt. So we can write Kt is equal to ln initial concentration divided by remaining concentration. So we can write K is equal to 1 by time ln initial concentration upon remaining concentration. So this is the expression of rate constant for a first order reaction. For half-life, this remaining concentration will be half of initial concentration. So we can write rate constant K 1 by this T will be T half, as we are calculating T half ln C naught upon C naught by 2. So we can write T half is equal to ln 2 upon K. So T half will be, the value of ln 2 is 0.693 divided by K. So if we know the rate constant for a fast order reaction, we can easily find the half-life for this reaction through this equation. And look at this expression. There is no initial concentration in this expression. So we can say that the T half of a fast order reaction does not depend on initial concentration of the reactants. So if we plot a curve T half versus concentration, as T half is independent of initial concentration. So we will find a straight line parallel to x-axis. Now we will talk about properties of first order reaction. Let's take the initial concentration is 100. After T half, it will be 50. For the next T half, it will be 25. After next T half, it will be 12.5. After next T half, it will be 6.25. So here 100 to 50, it is 50% drop. Here 50 to 25, it is also 50% drop. Here 25 to 12.5, here is also 50% drop. And 12.5 to 6.25, here is also 50% drop. So every T half, the concentration of reactant is dropping by 50%. So we can say that equal percent drops in equal interval of time. Let's take the initial concentration is C naught. After first T half, the concentration will be C naught upon 2. For next T half, the concentration will be C naught upon 4. So we can write C naught upon 2 square. After next T half, concentration will be C naught upon 8. So we can write C naught upon 2Q. After next T half, the concentration will be C naught upon 16. So that means C naught upon 2 to the power 4. So here is 1, 2, 3, 4. After 4 half-life, the concentration is C naught upon 2 to the power 4. So we can say after n half-lives, the concentration will be C naught upon 2 to the power n. So this property is very, very important, and these will help us to solve many critical problems regarding first order reactions. Now, let's take the expression rate constant K is equal to 1 by T ln initial concentration upon final concentration. We can also write A is equal to 2.303 divided by T log C naught upon Ct. As the reaction is A gives us products, initial concentration is A, initial concentration of product is 0. After time T, the concentration will be A minus X, and the concentration of products is X. So we can write rate constant K is equal to 0.303 T log initial concentration is A, and the remaining concentration is A minus X. We can also remember this expression for finding the rate constant for a first order reaction. So this is it for the derivation of some expression for first order reactions. In the next classes, we will discuss about different cases of first order reactions. So I hope everyone understands the concepts nicely. And thanks for watching the video. Don't forget to like, comment, and subscribe.